Hello everyone, welcome to the talk of 6Fit-A-Part, a protocol for physical distancing on a custom wearable device. I'm Yifeng Cao from Georgia Tech. The COVID-19 pandemic has increased people's awareness of the importance of public health. One of the easiest and the effective ways to prevent the virus spread is to maintain physical distancing. However, in crowded areas, such as hospitals or supermarkets, won't it be helpful to receive a friendly reminder if we venture too close to others? In this work, we hope to build such a system which can instantly warn a user if they get within 6 feet of others. An audio-visual alarm will trigger on the device in such cases. Such a system should achieve two goals. Firstly, the system should be low cost. We hope to build a system which is infrastructure-free, that is without deploying sensors in the environment, and reconfiguration-free, so that it works efficiently even when only a subset of devices are together. To achieve this goal, we decide to build a distributed system on the embedded devices with low deployment and maintenance cost. Secondly, the system should be lightweight. Being lightweight makes this system easily hidden in daily items, such as shopping cart, an identity card, or a smart wristband. However, building such a system is non-trivial. There are at least 4 challenges. Firstly, the computation resource is limited. We must make sure our algorithm can run smoothly on devices which has only tens of kbs of memory with very limited power. Secondly, we need to achieve peer-to-peer ranging with dynamic participation. Specifically, nodes should be able to enter and leave the network arbitrarily without interrupting the running of the algorithm. Thirdly, the real-time ranging is hard. In the distributed system, if every node needs to measure the distance with every other node, the time complexity of this algorithm is inherently O(n)². That means we have to deal with each step in the ranging process very carefully to reduce the time cost as much as possible. Finally, to deal with the complex wireless environment is very hard due to the uncertainty of wireless communication. To overcome the above challenge, we propose 6Fit-A-Part. 6Fit-A-Part is a physical design for real-time physical distancing on wearable devices. The prototype of 6Fit-A-Part is shown on the right in this slide. 6Fit-A-Part has 3 key on-device functions: an ultra-wideband radio-based ranging algorithm, a robust and efficient P2P protocol, and an occlusion detection module. Here is an overview of 6Fit-A-Part. At the lowest level, the UWB module deals with the ranging algorithm. It decides what method to use for distance measurement and what information the lower level needs to provide for the upper level for analysis. Basically, this module will provide channel impulse response and the packet timings. Then, the P2P ranging protocol will accept the packet timings from the UWB module. It provides a robust protocol for the nodes in the network to exchange packet timings, which is required to compute the distance. In addition, there are 3 submodules in the P2P protocol to improve the time efficiency. They are a time slotting scheme, a slot adaptation algorithm, and a response again scheme. These 3 submodules can substantially decrease the multiplicative constant of the time complexity, which makes 6Fit-A-Part feasible in the real world. Finally, we have an occlusion detection module. This module deals with the complex environments. It classifies 3 basic cases: a line of sight signal, wall blocking signal, and human blocking signal. This module reads the channel impulse response from the UWB module and the road distances from the P2P protocol, and then extract a couple of features. These features are used to build a tree model to classify the three different types of occlusion, so 6 feet apart can deal with them correspondingly then. Let's first talk about the UWB module. We choose UWB as our basic signal for distance measurement because it has several good properties. Firstly, we can quickly get distances with tens of centimeters error. By averaging multiple packets, this error can be reduced to 10 centimeters, which is enough in our M scenario. In addition, UWB has 1 GHz of bandwidth, which makes it defensive to the multipass. Finally, it has nanosecond time resolution, making it easy to directly compute the distance from the time of flight. Basically, distance can be computed directly by multiplying the time of flight with the speed of light. However, since two nodes don't share a common clock, they are not synchronized very well and have tens of milliseconds offset in the time of flight. This will incur huge errors. To mitigate the effect, we adopt the two-way ranging from IEEE 802.15.4. It is a widely used protocol in time-of-flight-based localization technique. Suppose there are two nodes in the network, A and B. A first sends a poll to node B. Node B will reply with a response message. After A receives a response from B, it sends the final message to B, so B can compute its constant at its end. During this process, we get 6 packet timings, TA1 to TA3, TB1 to TB3. Then we can derive 4 time durations, DA, DB, RA, RB. With these time durations, we can compute the distance directly from the formula shown in the slide. This rather non-intuitive formula has been adopted from the reference shown at the bottom of the slide. However, what works for a device pair doesn't necessarily scale to multiple users. There are two problems. The first problem is the medium access coordination. In a distributed system, a node has no knowledge of which other nodes exist near it at the very beginning. Without any coordination policy, the packet transmission will be in a mess with significant collisions because every node tries to send wireless packets arbitrarily. Secondly, if we naively perform sequential two-way ranging, it will take a long time to perform all the pairwise distance measurements. Notice that every distance measurement needs 3 packet transmissions. If we try to perform P2P ranging, the number of packet transmissions will be huge, resulting in seconds of lag in the real world. It's unacceptable. We will use a P2P ranging protocol to solve these two problems. Firstly, to reduce the time cost, we will use the broadcasting nature of the wireless signal. Instead of sending a pole and final independently to every other node in the network, the transmitter broadcasts pole and final to the whole network. By doing so, the number of packet transmissions will be reduced to 1/3 of the original. However, broadcasting brings a new problem, which is collision. Because of the feature of broadcasting, every receiver will receive the message almost simultaneously. If they directly respond to this message, they will have a great chance to collide with each other. To mitigate this problem, 6Fit-A-Part uses time slots. At the very beginning, the transmitter will send a number indicating the number of slots within which it expects responses. After the receivers accept this pool message, they randomly select one time slot from the pool and send a response message. By doing so, we reduce the probability of collisions. Of course, given a finite number of time slots, the probability is never zero. There will always be some random collisions. In a 10-node network, the collision rate can be as high as 50% if we fail to select a good value of the number of available time slots. Basically, we propose two solutions to make the protocol more efficient. The first solution is a slot adaptation algorithm, which can dynamically select the optimal value for the number of slots in every iteration. The second solution is a two-round P2P ranging scheme, in which nodes that collide receive a second chance at sending the response. The purpose of slot adaptation is to maximize efficiency. The number of slots should be neither too large nor too small. Probabilistically, the collision rate is coupled with the number of nodes in the network and the number of slots we offer. That is to say, if we observe a certain collision rate, and we can approximately estimate the network size, this will give us a hint to what number of slots we can offer. In other words, the network size can be estimated from the slot occupation rate of the received responses in the first iteration. Using this estimated network size, together with the collision rate, we can make a informed decision about the number of slots to offer in the next round. The other solution to the collision problem is a response-against scheme. When the receivers try to send the response to the transmitter as a reply, some of the responses, like response from user 4 in the slide, will be received successfully with no collision, but other responses will experience a collision because different receivers choose the same time slot. Whatever, the transmitter will collect all the responses which are successfully received in this round and put them into a receiving list. This receiving list will be attached in the final message. Then, the transmitter sends the final message. When receivers receive this final message, they will check to see if they are in the receiving list. If they are, they know that they succeed in sending in the first round, and we will stop it from running and let it go to sleep for a while to save some time and computational resource. Otherwise, if they found they are not in the receiving list, they will get the second chance to send the response again message. After a certain time, the transmitter will broadcast the final again message for these users to complete the distance measurement. Let's briefly summarize what we have done for now. What we already have is a low-level ranging algorithm and a robust protocol with which we can obtain the pairwise distance efficiently and accurately. However, we want to ask this question: should all distance measurements be treated equally? Actually, it's not true. That's why we have our occlusion detection module. Remember that we basically classify three different kinds of occlusion: line of sight, which means there's no occlusion, wall blocking, and human blocking. In the wall blocking case, it's very natural to think that the system shouldn't warn the user even if he is in the 6 feet range from another person on the other side of the wall, because there is no risk of infection. To differentiate wall blocking case, we observe that in the channel impulse response, the signal amplitude is much lower when there is a wall blocking. That is an important feature to distinguish it. In the human blocking case, we still need to warn the user when he is too close to others. However, the distance measurements are erroneous when there is occlusion, so we should compensate the distance measurement before the system gives a warning. Similarly, we use channel impulse response to differentiate the human blocking case. We observe that signals in the human blocking case not only have a lower power, its main lobe is also distorted by some closely coupled multipasses. It's a feature we use to distinguish the human blocking case. Based on the above observations, we firstly extract the channel impulse response in the lowest level. Then we extract a couple of features from the channel impulse response. We use these features to build a decision tree to classify the occlusion cases and build a regression tree to compensate for the erroneous distance. All these functions are integrated in the small embedded device with no cloud or internet connection. We implement and evaluate 6Fit-A-Part on Decawell Track 1000 toolkit and Adafruit Feather M0 with DW1000 chip. We use the arbitrary two-way ranging as the baseline. It is the original two-way ranging from IEEE 802.15.4. We focus on three metrics: percentile of rangings completed, average ranging time, and classification accuracy. We first look at the percentile of rangings completed. As we can see, in a 10-node network, 6Fit-A-Part can still achieve over 60% accuracy. For arbitrary two-way ranging, it is very hard for it to do any valid distance measurements. Then let's look at the average ranging time. Even in a 10-node network, 6Fit-A-Part can still achieve 1 second ranging time on average, which means that it can obtain the distance from all the other nodes in the network in 1 second. It corresponds to a 10 Hz ranging rate. As for arbitrary two-way ranging, the performance is much worse. Finally, we evaluate the classification accuracy in occlusion detection. We test in 3 different environments, corresponding to the low, medium, and high multipass level. Generally, we can achieve over 85% accuracy in classification. We also observe that with increasing multipass, the accuracy degrades a bit. Most of the misclassification happen between wall blocking and human blocking. There are some future work for 6Fit-A-Part. We plan to deploy 6Fit-A-Part on a large scale in the real world, such as grocery stores. We hope to collect large amounts of data to see if there would be any improvement. We also want to try with more sensors such as IMU, to see if we can make the system more user-friendly in interaction. To conclude, we designed a robust P2P ranging protocol with an average ranging rate of 10 Hz. We analyzed the channel impulse response to differentiate occlusion, enhancing the feasibility and generality of 6Fit-A-Part. We design and prototype 6Fit-A-Part on the embedded devices, featured by low power, lightweight, and small size. Thank you and stay safe.